Welcome back to chapter 31. We're picking up where we left off. So we're going to look at some various decay processes. One common form of radioactive decay is when a nucleus has the wrong balance of protons to neutrons and maybe too much energy, it can give off an alpha particle. Alpha particles are made of 2 protons and 2 neutrons, and we symbolize them with the Greek letter alpha, which you can see right here and also right there. Or we can also symbolize them with helium-4 because the helium-4 nucleus has 2 protons and 2 neutrons in it. All right, so alpha particles are big and bulky and they have a charge, which means they can be stopped by air. They're not especially dangerous in that regard, a little distance and you're probably pretty safe. You just don't want to eat them. Don't worry so much about the decay scheme. I'm going to show you how to figure out what isotope the daughter is. So we always start out with a parent. If it gives off an alpha particle, then you have a daughter associated with that decay. So let's look at a specific example. We have element 61. And in fact, we have promethium 145, so that's element 61. The 145 is the atomic mass number. The 61 is the atomic number. Atomic mass numbers are always superscripts. Atomic numbers are always subscripts. And we know we want it to give off an alpha particle, and what we're interested in is what is the daughter? What is the daughter element? So we have to find out 2 things. What's going to be the mass for the daughter and what's going to be the atomic number or charge on it. So for the mass, we look at the superscripts, the upper numbers. Promethium 145, that would be 145. If you take the arrow and replace it with an equal sign, so we've got 145 equals on an alpha particle, the atomic mass is 4. So we put 4 as our atomic mass number, and we don't know what the daughter has for it. But to figure this out, you just subtract 4 from both sides and you find out that the daughter's atomic mass number is going to have to be 141 because charge and mass don't just disappear. We have to keep up with our nucleons and our charge in these decay processes. To find out what the atomic number is going to be, you look at the subscripts, the lower numbers. So 61 for the promethium. The alpha particle has an atomic number of 2 because remember it has 2 protons in the nucleus. And so we're trying to find out what would be the daughter's number of protons. Well, 61 minus 2 would give us 59. So we know the daughter has 59 protons and 141 nucleons. We would look up 59 on the periodic chart or look it up in Appendix A. If you did, you would see that it is PR. Please don't ask me to say that. And so the daughter is PR 141. So you can write it this way, or you can say PR 141, or you could write out the name if you wanted to. So this is a little snippet of Appendix A, which I've attached to the first part of chapter 31 as a PDF, and it's also in the online book. And if you were in class, you got a hard copy. So you can see we have the column for the atomic number, the name, the atomic mass number, and the symbol. You need to be able to locate these in the chart as we go through. So the energy released during decay is called the disintegration energy or the Q value. You need to remember that protons, which are crammed in the nucleus along with some neutrons, protons would repel each other, so the nucleus shouldn't exist, but we know it does. And so we assume that the energy that holds it together is the binding energy. We talked about that when we talked about binding energy. Well, if you take something out, it removes energy also. So let's look at the Q value for an alpha decay. The Q value for an alpha decay would be the mass of the parent minus the mass of the daughter minus the mass of the alpha particle. So mass of parent minus mass of daughter minus mass of alpha particle. For the alpha particle mass, we will use the mass of helium-4, and you would look it up on the first page of Appendix A. We'd use the mass of helium-4. So suppose we wanted to know what the Q value was for what we've just done. The parent was PM145. So we would look its mass up in Appendix A. The daughter was PR141. We would look its mass up in the Appendix A. And we've looked up the mass of the alpha particle. So we ought to be able to take those three masses and calculate the Q value. So the Q value would be the mass of the parent minus the mass of the daughter minus the mass of the alpha particle. Plug those three numbers in, do the subtraction. And then to convert unified atomic mass units to MeVs, we multiply by 931.5. And that gives us a Q value of 2.32222295. And it's measured in MeV. Remember, MeV is million electron volts. It's a unit of energy. So anytime we've got four variables in this equation, the Q, the mass of the parent, the mass of the daughter, and the mass of the alpha particle. If you know three of the four, you can calculate the fourth. Sometimes I'll give you the Q value and the mass of the parent, and you'll have to calculate the mass of the daughter. So it's not always just calculate the Q value. We did an example like that in class. So let's look at beta decay. Beta decay is when the nucleus, we've got two types of beta decay, beta minus and beta plus. So in beta minus decay, a neutron changes into a nuclear electron and a proton. The proton stays behind in the nucleus, and the nuclear electron gets ejected as a beta minus particle. So beta particles can be stopped by paper. They're a little more energetic than alpha particles. They travel a little farther. Don't worry so much about the decay scheme, except to notice that this little symbol right here is an anti-neutrino. It's the Greek letter nu, so it looks a little bit like a V, but you'll notice on the right-hand side, it doesn't extend out. It sort of curls back with a bar over it. So this is an anti-neutrino. It was named by Enrico Fermi in 1934, and what it does is it carries away energy that the beta minus doesn't. It was developed out of necessity. They studied beta minus decay, and they were almost right in their answers, but a little bit was missing, and so they said, okay, let's assume there's something we don't know yet. Excuse me, taking energy away. So the anti-neutrino has zero charge and very little rest mass, and it just removes just a teeny bit of energy from the decay process. It does have a Q value, beta minus does. We're not going to use it. You won't be expected to calculate with it. So let's look at a beta minus decay. Suppose you have sodium-24 giving off a beta minus. What's the daughter? Well, we look at the mass numbers, 24 for the sodium-24. Beta particles have zero mass, and we don't know the mass of the daughter, but when you do the arithmetic, you find out that the daughter has the same mass as the parent, 24. Beta particles do not change the mass of the nucleus, so the mass of the parent and the mass of the daughter will always be the same for beta minus decay. The atomic number of the charge is going to be different. So that'll be the atomic number was 11 for the sodium. For the beta minus, it is a -1, and we don't know what the daughter is. So to get rid of the -1 on the right side, you have to add 1 to both sides, which means our daughter has to have an atomic number of 12. When you look up 12 in Appendix A, you find that it's magnesium. So the daughter is magnesium 24. In beta plus decay, sometimes called positron decay, a proton changes into a positive nuclear electron and a neutron. So again, the mass isn't going to change, but the daughter element will not be the same as the parent element. And in this case, you'll notice instead of a mu with a line over the top of it, it's just a mu by itself. That is a neutrino. That's the particle to the antiparticle mu bar. So when you put the bar over the mu and make it an antineutrino, antineutrinos are antiparticles, neutrinos are particles. Every particle has an antiparticle, and we'll talk about that a little later. The neutrino was suggested by Wolfgang Pauli in 1930 to reconcile that missing energy I mentioned earlier. It also fixes differences in linear momentum and angular momentum, and takes care of the things we couldn't explain any other way. The neutrino is interesting. We have studied it. It travels at the speed of light, so that's what little c is, remember. It has a 0 electric charge. It has a really tiny rest mass. It doesn't weigh very much. It has spin of 1/2, and it interacts very weakly with matter by way of the weak nuclear force. So it has an interesting array of properties. There is a Q value for beta plus decay, but we're not going to calculate with it, so you don't need to know that formula. You do need to know how to figure out what is the daughter if you have beta plus decay. So suppose we have nitrogen 13 giving off a beta plus particle. We want to know what's the daughter. So if you look at the masses, you'll find that the mass of the parent and the mass of the daughter are the same. Beta decay, doesn't matter if it's beta plus or beta minus, does not change the mass. So what we start out with is what we end up with. However, the charge does change. So we started out with nitrogen, that has 7 protons. And the beta plus, that would have to be a +1. And then the daughter is our question mark. So the question mark ends up being 6. There have to be 6 protons in the daughter. And if you look up element 6 on the periodic chart, you find, or in Appendix A, you find that it is carbon. So our daughter element for nitrogen 13 decaying by positron emission, the daughter element would be carbon 13. Electron capture is not exactly beta decay, but it is related. In electron capture, the nucleus absorbs one of those K-shell electrons. So it is sometimes called K-capture. You don't need to know the decay scheme. You don't need to know the Q value, and you don't need to know how to find the resultant. If I ask about what is electron capture, it's sufficient if you can tell me it's when one of those K-shell electrons gets absorbed and then decay takes place. Gamma decay, you do need to know about. So with gamma decay, you have an unstable nucleus. It's not so much the ratio of protons to neutrons, but it's just got a little too much energy. And so in this case, in gamma decay, gamma is a form of electromagnetic radiation. And so the energy is just given off. Gamma rays are very dangerous. They can travel through lots of air, lots of water, lots of paper. However, lead can stop them, but you do want to be really careful. So let's look at decay. If you had sodium 22 giving off a gamma ray, what would you end up with? Well, you'd end up with sodium 22. It would just have less energy. Sometimes, to show that it's in the excited state, they'll put an asterisk, one of these little stars on the parent to show, hey, it's a little too energetic. And when you come up with the daughter, the star is missing. So gamma decay, what you end up with is what you started out with. We'll look at the magnetic separation and then move on to something else. So with magnetic separation, you can take alphas, betas, gammas, neutrons, and pull them apart from a beam based on the fact that the beta plus and the beta minus and the alpha have different masses and charges, that gammas and neutrons don't have charges. So let's look at this. A gamma ray and a beam of neutrons, they don't have a charge. And so they're not going to be deflected by the magnetic field. You'll notice in my magnetic field, I have a negative charge on the left side and a positive on the right side. So the uncharged things go straight through. Negatively charged items will be attracted to the positive. So that is why we know that the one beam that goes to the right is going to be the beta minus. To the left, where we have the minus, would attract anything that has a positive charge. So that would be the positrons, the beta plus, and the alpha particles. Well, how do I know which one is the alpha and which one is the beta plus? Beta particles are really teeny tiny, and it is easy to deflect them because they're very small. So beta particles get pulled over the most. They'll have the greatest deflection angle. Alpha particles are bigger and heavier, and they don't get pulled as far over. So that's how we tell them apart. And here's a little graphic from the textbook showing you a very similar process, except they're showing north and south, and I really like the plus and the minus. All right, we will stop here and then we'll pick up in the next video to discuss radioactive decay processes. So we'll stop with this, stop the share, and stop the recording.